Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020. And this is the first continuation of the lecture, Fundamental Theorem of Calculus, FTC 1. When I left you last, you were evaluating these. I hope you finished them, but if not, I'm giving you time now. You know what to do. Let's see how you did. All right, here you just are having an indefinite integral, so your answer is going to be a family of functions, not a number. This is not a definite integral. So you add 1 to the exponent, divide by the new exponent, minus. You add 1 to the exponent, and you divide by the new exponent. The new exponent was the minus, where that came from, plus c. And so that's what you got for the first one. Now the second one is a definite integral, and we are going to be using the fundamental theorem of calculus. So we're integrating the definite integral from 1 to 2 of the same integrand. So you see what we did is we integrated this. Recall we can use the constant of c to be 0 here, and then evaluate this as 2 minus evaluating it 1. So I'm evaluating it 2. This minus sign is that minus sign. This minus sign here is from the fundamental theorem of calculus, and it's minus the whole of this business evaluated at 1. I simplify that, and I get 17 over 6. Now, number c, and you have to be careful here, but the integral is here to make a point. Recall that in order for us to do an integral, the integrand must be continuous within the range of the limits. In this case, the second term will have division by 0 at y equals 0. And since y equals 0 is in the interval of integration, it's not continuous, and we can't use the fundamental theorem of calculus to evaluate that integral. Now notice this is different than what we did in this problem, because 0 was not in this interval of integration. So here's another problem. More algebraic functions. You know what to do. Let's see how you did. So the first one, you do term by term. You should have gotten 2x cubed minus 5 halves, x squared plus 2x for your integrand. You evaluate at the top level minus the integral evaluated, the antiderivative evaluated at the bottom level. So here is, I plug in the top values of 1 minus this minus sign is from the fundamental theorem of calculus. I plug in minus 3. Be careful with your signs here. And you should get 84 for your answer. I think this was the next one. On this one, you should do algebra before you do the calculus. So we distribute this square root of t throughout. I think actually we did a problem like this in indefinite integrals. But you get this minus that. And now you find the antiderivative of each term. And you evaluate at the top endpoint minus the bottom endpoint. Now when I put t to be 0 here, I'm just going to get 0. So then it's going to be 0 minus. And this is what I get when I plug in 4. Notice that it's minus 4 times the whole of this integrand, and you get a negative number. Now a negative number is fine, because that just means that the area is underneath the x-axis. Or said another way, the net area is underneath the x-axis. Here again, we need to do algebra before we do the calculus. So we divide that m squared into each one. Again, I think we did this kind of problem before. And so we get this after we do the algebra. And now we will go through and find the antiderivative of each term. Notice the absolute value here. Sometimes it's important, and so we'll use it most of the time. And here we get this, and we're going to be evaluating this at 2, subtracting off the value at 1. Again, the constant of integration is going to be 0, and that is okay. So then I plug in the 2, getting this. This minus sign is from the fundamental theorem of calculus, and I plug in the 1 and get this. Now remember that the natural logarithm of 1 is 0. And so I do the calculation and get 9 minus the natural logarithm of 2. This is the last one of those. We're just integrating 1 dr. That's going to be r. I plug in the points and subtract, and I get minus 35. Here's example 3. You're supposed to evaluate all this functions, and you see that we have exponentials. We'll eventually have some logarithms here in these problems, I guess, and trig functions. So you know what to do. Let's see how you did. So here you just do term by term. This is the antiderivative of that one. This is the antiderivative of this one. Evaluate at 1 and 0. Notice that when I put 0 in, I'm going to have 0. So I'm really just putting 1 in there. I get this, and that is my final answer, minus 8 over 5. Here I do this term by term. So the 2 I pull out, but the antiderivative of the sine of theta is minus cosine of theta, and the antiderivative of the cosine is sine of theta, and I'm evaluating this at the endpoints pi over 3 and 0. Again, you're not using calculators, so you want to be familiar with these special angles. So we substitute the top, pi over 3 in. This minus sign is from the fundamental theorem of calculus, and it's minus the whole of this evaluated at 0. Now the sine of 0 is, of course, 0. The cosine of 0 is 1. So you do all the arithmetic, you get this, you combine like terms, and you get this for your final answer. Again, you do it term by term, so the antiderivatives are going to be 5z minus 2 times the secant of z, evaluated at these 2 points. So that is going to be 5 times the I'm substituting in the top limit for z, and the top limit for z. Here is the minus sign. This minus sign is from the fundamental theorem of calculus, minus the whole of evaluating that integrand, or that, antiderivative at pi over 6. And I plug in all the numbers. Again, those are special triangles, and you get this as your answer. Again, there are no ugly numbers, just like there are no ugly babies. Here we're doing this term by term. Now notice here you have an e to the minus z in the denominator, so the net of that is going to be e to the z. So the antiderivatives are going to be 3e to the z minus 1/3 the natural logarithm of the absolute value of z. And I'm going to substitute minus 1 and minus 20. This minus sign is from the fundamental theorem of calculus. Notice the absolute value makes a difference here and here. So I do the arithmetic, and I get 3e to the minus 1 minus 3e to the minus 20 plus 1/3 the natural logarithm of the absolute value of 20. This is a number, and this is what you would reach with your final answer without a calculator. The last problem, if you look, we're integrating from minus 2 to a positive number, and so you see 1 over t blows up there because you can't divide by 0. So this integral, again, can't be done. You can't divide by 0, and 0 is in the interval of integration. The fact that the first two terms can be integrated doesn't really matter. It blows up, and the entire integral cannot be done. Okay, here's a problem called number 4. You have f of x being defined as a piecewise function, like over here. We're supposed to evaluate these two integrals. And so we have a and b. You know what to do. And we'll see how you do in 36.2.